For the rest of this chapter, we look at estimating cell total capacity. And we've seen some methods for estimating capacity so far, such as the Kalman filter methods. But we're going to find out that these methods are biased and what that means and why that is. And we're going to develop a method that's not easily implementable in practice, that is not biased but is optimal. And then we're going to develop a method that approximates that optimal solution but is quite easy to implement in practice. So we're going to fix our capacity estimate throughout the rest of this chapter. Part of the issue is that going back to the beginning of this chapter, we talked about sensitivity of cell voltage to different parameters we might want to estimate. And we found that the sensitivity of cell voltage to cell capacity was very low, which means that if in the voltage signal, the signal-to-noise ratio, if you want to think about it that way, is very low. And it's hard to extract the signal from the noise, the true capacity from measurement noise and other kinds of noises. Using something like a Kalman filter-based method does some help, because it attempts to minimize the impact of noise, essentially by averaging over many time steps to make its estimate. But it turns out that in the process of averaging over many time steps, it's introducing an offset into the solution, a DC bias into the solution. Here we're going to at least discuss the origin of the problem in this section, and over the next sections we're going to talk about, well, how do you deal with it? How do you remove this problem? We start by looking at the Coulomb counting equation, the state of charge equation in continuous time. Of course, we could do this in discrete time too by replacing the integrator with a summation, and nothing really changes in what I'm going to say if we do that. So we have here that the state of charge at time 2 is equal to the state of charge at time 1 minus 1 divided by capacity times the integral of current. And we can rearrange this, to be z at t2 minus z at t1 equals minus 1 over q times the integral, and then multiply both sides by q, and we get this equation here. So negative integral of current equals q times the difference in state of charge. I want us to think of this equation, or this part of the equation, as a computation that results in some variable y. The current is something we measure. The Coulombic efficiency hopefully is something that we know and is not changing, so I can compute the left side of the equation and call it y. And on the right side of the equation, I want us to think about this as some variable we might call x. We are estimating state of charge using methods perhaps from the previous chapter. So I have an estimate at time 2 and an estimate at time 1 of state of charge, and I difference those to make the x variable. And if we think about them as y and x, I have this simple linear equation, y equals q times x, and q is the slope. If I were to plot a lot of x points of difference in state of charge and y points, the accumulated current between state of charge estimates, I would get ideally a perfectly straight line, and the slope of that line is q, the capacity. So if we think about it that way, you say, oh, well, finding capacity is simply a matter of fitting a straight line to some data. It's a linear regression. And linear regression is something that's quite well understood, quite well known, and we can use any of the linear regression methods to fit this straight line and to fit capacity. There's a problem, though. Using standard regression techniques, which are least squares regression techniques, the problem is that standard least squares expects noise in only one of the dimensions. It expects your x values to be perfect, but your y values are permitted to have some noise. And so we could think of having error bars on y because of noise. Whether I know what the error bars are or not, there's some variation in the measurement that could have been made simply because there's noise, but there's no error bars expected in the x. Basically for us, what that means is the assumption, if we use least squares to estimate capacity this way, the assumption is that our state of charge estimate is perfect, completely perfect, no inaccuracy at all. One way we can think about this, maybe a little bit more mathematically, is the least squares problem tries to find the solution to this equation. It's saying that there could be noise on y. The noise is delta y. I don't know what the noise is necessarily, but I assume that the delta y is random, but on average it is 0. And I find some q that minimizes the squares of y away from qx, even in the presence of this noise delta y, this zero mean noise delta y. That's not the problem we have. We have this problem right here. We have the problem that there happens to be noise on y because I'm integrating a current sensor that is not perfect. So yes, we admit that there is noise on y, but we also admit that there is noise on x because x is the difference between state of charge estimates. And your experience with state of charge estimators from the previous chapter should let you know that those estimates are pretty good, but there's still error, and it might be 1% or 2% or 3% or whatever it is, but there's some error on x, and it's not actually insignificant. If I'm doing a total capacity estimate problem by integrating the left side, we know that the noise on the left side is going to increase over time, at least in variance. The noise on the right-hand side may be constant over time. So that might lead us to think that, oh, in some cases, maybe I could get away with least squares or not get away with least squares. We can actually think about that a little bit, but never will the least squares method be solving the problem that we actually have. So state of charge estimates are generally imperfect, always. There will be noise on this x variable, which is the difference between two state of charge estimates, and using standard least squares linear regression results in an inaccurate and biased estimate. And you say, okay, I'm not doing least squares, I'm doing Kalman filters. Well, Kalman filters are recursive least squares estimators. A least squares estimator would take, as we drew this picture before, it would collect data. Every time I had a new data point, it would add one more point to the set, and I would have an ever-increasing memory of data points. Well, the Kalman filter is a clever way of not requiring that you remember all those data points specifically. It wraps that new data point into what it's already computed to compute the least squares estimate. And if the data points are independent from each other, if the noises are independent, that is, then it's exactly the same thing as standard least squares, just done in a recursive way that's computationally efficient. So Kalman filter methods are least squares methods, and so they are going to have this problem. How do people deal with this problem? Well, the typical approach is to try to make sure that the SOC estimates don't have noise, or that they minimize the noise as much as possible, and then still use least squares estimates because that is what most people know how to do. For example, we could force cell current to be 0 before the test begins, so that the cell is in an equilibrium state, so that we know there's no diffusion voltages and so forth. So I can make as accurate an SOC estimate as possible, and whatever I do during the test happens, and then I rest so that I'm also in as close to an equilibrium state as possible, and use this SOC and this SOC and the integrated current in between to make my SOC estimate. Often we try to do that over as long a period as possible so that I can integrate a lot of ampere seconds to make the noise in the X variable as little as possible, to actually expose capacity as much as possible, thinking about the sensitivity analysis we did at the beginning of the chapter. So maybe while I'm plugged in and charging, if that's a possibility in this application, we could do that. So this procedure is going to eliminate to a large extent, but it's still not completely, error in this X variable. It's going to make regression reasonably accurate, but it's still not going to be perfect. It will still be biased by any residual noise that we have in the X variable. So is there a solution? Are we doomed? Well, we're not doomed. This, even using least squares under these controlled conditions, can provide capacity estimates that are not too bad, although we will look at some examples by the end of the chapter that show that the bias might be larger than you think it is. There is a solution, and that is a method called total least squares, which replaces the ordinary least squares solution. It's simply a different way of optimizing data sets for regression. Ordinary least squares assumes we have noises on the y variable only. Total least squares says that I've got error bounds in both dimensions, in x and y, and it takes both of them into account when it's finding its solution. That's what we're going to be looking at over the next few sections, and we'll come up with a way of estimating capacity that's not biased by the errors in the state of charge estimate.